with that topic. Okay, we got two more. What's the time? We got the time?
And it is, I think,
1:12? Okay. Excellent. I want to talk about two more special cases. I'm not going to work any of the math problems today on that math practice page. I'm going to let you just see how it goes. You can try. You can do it on a separate sheet if you want to. But I'm probably just going to do the conceptual stuff today, and then we'll do the math a little bit at the beginning of the next class, and we'll have that one extra class too after we finish Newton's third law. I don't think it'll take us the whole time to talk about the third law in the next class, so we'll be able to do that then. All right, I'm going to talk about a special equation. We've got net force is equal to mass times acceleration. And we're also going to look at a similar equation, or really the same equation, W equals mg. So what's W in this case?
Weight.
The weight. And, oh, there we go. And then m is mass, and g is
Gravity.
an acceleration of gravity, right? So this is the only other equation you're going to have in this unit that we haven't done already. You're still going to have to do a little bit of kinematics in the unit, so I don't want to say you're not going to do any math besides these two, because that acceleration we can still play with kinematics. But this equation, I didn't write on your yellow sheet because it's really the same equation. So weight is a force. We've been labeling it as such in all of our free body diagrams. It's a vector, it points downward. It's the force of gravity on a given mass. And this is it in equation form. It's so pretty. So weight, downward, gravity is an acceleration acting downward. And we can then turn that acceleration of gravity into a force of gravity by using this equation. So the thing I want to point out is kind of an interesting bit about weight and mass and what they really are. So can you tell me what do you think mass is?
It's not like the weight, it's because it's not. It's like weight, but
It's related to weight. Obviously, they're in the same equation. So the bigger the mass is, the bigger the weight is, right? So they're related. I think of it more as a chemistry term sometimes, and that it's really just like how much stuff it makes you up, how much matter is present. Yeah. So if you added up all of the atoms in an object, then you would have its mass. So if we took, it's complicated for us because we've got a lot of things making us up, but if you had like a little chunk of copper and you added up the mass of all copper atoms, you would have the amount of matter in that chunk of copper. We could do the same thing with us. So it's a kilogram measurement. We measure it in grams or kilograms, and it's the matter that's present. But we can turn that mass into a weight by multiplying it by gravity. So how would it change if I had somebody like us standing on Earth versus someone like us standing on the moon? Are both of their quantities, weight and mass, going to be different? Is one of them going to be different and one's going to stay the same?
mass would be the same, but weight different.
Very good. Okay. Because the Earth has gravity of 9.8 meters per second squared, if this person has a mass of, let's say, 50 kilograms, we can take their 50 kilograms times the 9.8, and we could find out that they have a weight of about, is that 490-ish newtons? Something like that. So their weight would be around 490 newtons here on Earth. Their mass was 50 kilograms. If they got on the new SpaceX BFR thing, they paid a whole bunch of money, they got to go to the moon, which somebody's going to do. I haven't looked up who that person is, but they announced who it is recently. The first person, paying customer to go to the moon. If they're on the moon, their weight is going to be different. The moon has gravity of about 1.6 meters per second squared. So on the moon, their weight is going to be different, but their mass is the same. So their mass is still 50 kilograms, assuming they didn't vomit a lot on their rocket journey to the surface of the moon. And then what would their weight be on the
It
moon?
would be
80?
I think.
Okay. 80 newtons, quite a difference in weight from the Earth. So the big idea here is that mass stays the same. No matter where you go. I'll just keep it big. I'll keep the neighborhood big in the universe, in the solar system, whatever. If you're orbiting in the space station around the Earth, you are weightless, which we'll talk about. But weightlessness really means that you don't have any weight relative to the thing that you're in, because you and the thing are moving at the same speed. Technically, you have gravity acting on you because it's keeping you in that circular path, but you're weightless. You still have mass though. So no matter where you go, weightless environment, planet, giant planet, little planet, your mass stays the same everywhere. And then it's the weight that's changing based on gravity. All right, now that we've talked about weight a little bit more, I want to discuss just a little bit. I know that, I didn't bring my book. I guess I'll do that next class. I was going to do a little demo, but I didn't bring the book I wanted to bring. I traveled light today. Okay, let's do my last topic, which is things falling. Now that we've talked about weight, let's look at some things jumping out of airplanes. Have you ever been skydiving?
Nope.
I think either. It's on the to-do list every day. I should probably do it while I can still enjoy it. I get mad because I used to love all kinds of amusement park rides, but now as my inner ears have gotten older, I can't do the spinning stuff. Anything that spins too much, I just can't enjoy anymore. So it's a bummer. I don't like it. I still like roller coasters, but I can't. I got on those the new swings at Six Flags, new relatively speaking, like 5, 6, 7 years old. But it's like too tight a circle. I was just like, I could not hang with the kids on that ride. Okay, I'm gonna have somebody jumping out of an airplane. Where's the door? Here's the door, I guess. That would be behind the wing. I'm not really sure. I should make some windows. Okay, airplane flying, person jumping out of airplane. And I'm gonna use, this is again on one of your CP pages on the back. There's a good chat, a little thing that you're gonna go through and work out some numbers. I just want to talk about it real quick. So if I have a person who jumps out of an airplane, they're right here in the doorway, and they got their little backpack, their little parachute backpack on, and they're ready to jump out. Right as they jump out of the airplane, they're so happy, their little hair's blowing up in the air. Okay, what force is acting on them?
They have weight or gravity.
They have weight acting downward, right? Right as they jump out, like right initially, they're hardly even moving. Technically, they just stepped out. Is there any other force acting on them?
There'll be something going to I guess there's still be the movement from the planet.
Okay, so if the plane were going this way, right? We talked about that frame of reference thing. If the plane's going to the right, they also are going to be moving to the right. Now, we haven't done projectiles, but technically, once their foot leaves the plane, then the plane is no longer forcing them in that direction. They're still going to have some velocity in that direction, but there's no force acting that way. So once their foot leaves the plane's going to fly off, and then they're gonna end up just falling. So they're technically only force acting on them at the very beginning is weight, that's it. So anytime I have something, once I let go of it and let it drop, the only thing acting on its weight, with the exception of, there's a little
slight,
bit,
small, normal force of.
and now is it a normal force or is
It's a
it,
friction.
it's an air resistance or air friction? So that's gonna start happening to my skydiver. It's just not happened yet. And there's certain objects, and that's what I was gonna do a little demo, and I didn't bring. You have your book. Okay, let's do it with your book. And I have a, piece of paper. Okay, so I know that Galileo had talked about he dropped the different objects off of the Leaning Tower piece. And everybody thought, because Aristotle said, heavier objects fall faster than lighter objects, for 2,000 years people were like, yeah, they do. But they don't, right? He dropped both of the heavy and the light object off, and they both hit the ground at the same time. But one of the reasons why is because they were dense. They were pretty dense and compact, and they had similar air resistance, or very little air resistance. If I take two pieces of paper that have the same weight downward, I have a fan blowing on me, so this might affect it, and I crumple one of the pieces of paper up, are they going to fall at the same rate?
I want to say no, because that acts like a friction.
Okay, because basically they have the same weight, but one of them is going to be more resistant to falling, right? So my big piece of paper has a lot of air resistance. It acts like a feather and it kind of floats down. This is more compact. Is there a way I could get this paper, I'm going to borrow your book now, to fall like a book? Because obviously if I drop, the book is very heavy, right? Woo! So we know the book's going to hit the ground first, because we know the paper didn't even hit the ground at the same time as its wallpaper friend. So how can I get the paper to fall fast without air resistance?
Maybe you could turn on the side.
You want to turn it this way, or can we do this? You think that's going to get the paper to fall, or will the paper blow out? Let's try it. Ready? Oh, it didn't blow out. Okay. And I don't think the video captured that. Not sure, but
I think it captured the fall. I don't think it captured the thing.
but the paper stayed underneath the book. Now, what if I do this? Now the paper's on top. What do you think is going to
I
happen?
say it's going to blow away.
You feel like it's going to blow away? But what if the paper, if I had a vacuum, if I could vacuum out the room, all the air gone, seal up the room tight, and there's no air in here, if I dropped the paper, it would fall just like the book, right? Do you think let's just do it. Let's see what happens. Ready? Oh, that's pretty cool. It didn't hardly budge. So for those of you playing along at home, try it. Just put a paper on top of a book. The book needs to be bigger than the paper. That's the key. If I had a big wide piece of paper, the edges would catch the air.
Yeah,
But
yeah.
Right? But the book is doing all the work. It's heavy enough that it's pushing the air out of the way. Which one is experiencing more air resistance when I drop them individually? The book experiences more air resistance. This has very small weight, and it can't experience any more air resistance than its weight, or else it's going to be like the refrigerator example where I was going to get crushed by the fridge. So if this has a weight of 0.05 newtons, it's only going to experience 0.05 newtons of air resistance. This might have a weight of 5, 10 newtons, so it's going to experience 5 or 10 newtons or less, probably. But it's going to experience more air resistance, so that means the book's really good at pushing air out of the way. So when you drop it, there, I didn't quite have it on, you saw the edge flutter up a little bit. So that's a good example of how air resistance works. It doesn't always, you don't always have higher air resistance in certain situations that you think you would. But in my first example, up here back to my skydiver guy, if I do acceleration equals net force over mass, the net force in this first position is just his weight, right? That's the only force acting on him. If I did the math, I would find that the acceleration was negative 9.8 meters per second squared. I think on your conceptual physics page it's going to say 10, or you'll get 10 because they use the rounded number. As my man starts to fall, or my lady, I'll make it a lady because I'm going to go skydiving too. As I start to fall, does my weight change? Probably not. I mean, unless I'm puking again, that would be weird. Nobody wants to do that on their first skydiving trip. But I'm going faster here because I've been accelerating at 9.8. The faster I go, the bigger what is?
Yeah.
I gotta give myself a smiley face. What starts creeping up?
The pressure.
The air resistance, right? So the faster I fall, so when I first jumped out, there was not any air resistance initially, but as I fall faster and faster, the air resistance, I'm going to just label with an R for air resistance because that's what the CP page uses. That becomes bigger. It's still not as big as the weight. So what's going on now? Is my net force going to be bigger or smaller here?
Net force would be small.
The net force is going to get smaller. So in this position, my net force is decreasing. And we know based on Newton's second law, if the net force is decreasing, what else is decreasing?
The speed.
The acceleration. Okay, so this is where our brains break a little bit. Because this is where we start having to tease apart speed, acceleration, net force. Like how is this working? My acceleration has got to be decreasing because my net force is decreasing. Newton's second law says whatever happens to F happens to A. But the whole time I'm falling, what's happening to my velocity?
Your velocity will be increasing.
Is it increasing or decreasing?
Assuming the acceleration is still there, you can still be increasing.
It is, that's right. So the velocity is still increasing, which makes total sense because everybody knows how skydiving works, right? We've all watched enough YouTube videos and things to know. Then you fall faster and faster as you fall out of a plane to a point. So I want to get to that point where we stop falling faster and faster. But this whole time, the acceleration is decreasing and the net force is decreasing. Your velocity is still increasing until you get to the magic point where, oh wow, there's a lot of hair blowing around. It looks like her leg's broken. Let me just take that off. Okay, now I've got weight acting downward, same weight, and she's fallen so fast that now the weight that she has is equal to the resistance that her body is experiencing from the wind. This is the point in time where like the person's face is flapping in the wind and they're like, and they've gone crazy. So weight is equal to resistance. What's my net force at this point?
Net force would be 0.
It would be 0. That's crazy, right? This is a case of dynamic equilibrium. This person is having the time of their life. They paid big bucks for this. It's exciting. But their net force is 0. It's the most exciting part of the fall. Their acceleration is 0, but they are falling their fastest. That's the fastest they reach, their fastest speed. So now the velocity is constant. It's the biggest it will be during the whole free fall experience. Not technically not free fall because they're not falling without air resistance. So it's the biggest value it'll be right now, but it's constant. It's not getting any bigger. This is a special type. It's got a name called terminal velocity is what they call that when you reach that balance between weight and air resistance. And then what happens when they open their chute?
They get a lot of air resistance.
Now all of a sudden, they get yanked up right? Their parachute starts to open. They have the same weight downward, so the whole time they're falling, they've got the same weight. But now they have this really big air resistance once the chute opens. And they're so happy. Look, they've survived. Their chute came open. They're very relieved. Now the net force is in which direction?
Net force would be up.
It is. It's upward. which is, we haven't talked about any of these cases today, so I wanted to bring this up. Air resistance is a type of air friction. If the friction or resistance force is larger than whatever force is applied or natural weight downward, then your acceleration is going to act opposite to the direction you're moving. And that's what deceleration is. It's the whole reason we brought the parachute with us. So you could have told me that it was decelerating because you understand how parachutes and free falling experience works out of an airplane. But when you see how the vectors and the forces work out, it's kind of cool. So the net force upward on the parachutist means the acceleration is upward. That's a deceleration. And that means the velocity is decreasing now. Which it should be, because we want to slow down a little bit. You'll eventually reach terminal velocity with a parachute open. It'll be a much smaller velocity than we saw here, thankfully, because you want to sail down at a safe speed that doesn't break bones. So this R will decrease eventually, but when you're going that fast, just like it took R a while to build, it takes R a while to decrease and match the weight again. So I just think it's a cool example of how you can have something whose the velocity is increasing this whole time to here, but the acceleration is decreasing at the same time. I feel like it really helps you to sort of understand how acceleration and velocity are related, but totally different at the same time. So I think it's a good one. Any questions about this? I think that's all. What time is it? 1:30. Okay, well what I might do, I think that's all.